Hi, everybody. So my name is Fabian, and I work at AMD on basically graphics architecture evolution. And specifically, I work on making the GPU more independent from the CPU by basically letting it schedule work onto itself without having to rely on the CPU to do that for it. And this is already part of our hardware in the graphics side, so it's called GPU work graphs. And my research focuses on kind of taking these mechanisms that are available and applying them to HPC workloads, such as sparse matrix vector multiplication, which I'm gonna take a look at now. So in SpMVs, we usually have very large sparse matrices, and we don't want to store all of the zeros, so we have a compressed format such as CSR, which boils down to a linear array of non-zero values, but this array actually encodes rows of different sizes, and that's exactly why SpMVs are difficult to map onto GPUs, because they are a very irregular data structure and we want to process them on a very regular parallel hardware architecture. So as we see here, the rows have different length and we have a lot of them, but the problem is that each one of them only contributes a single output value to the final vector that's the result of the SpMV. So if we go at this naively, we have the problem that, well, we could just allocate a single thread to each row, but obviously this will scale in runtime to the length of each row. And then we have the problem that we have very disbalanced threads on our GPU, so we end up not utilizing any of the hardware for a long time, and just a couple threads idling the entire GPU, basically. So a more ideal approach would be to somehow group the threads in a way that we actually have parallelization within each row, so we can have parallel reductions in the longer rows and only use a couple of threads for the shorter rows. Now, this would be nice to do, but the problem is that only the CPU can actually launch threads onto the GPU. So we have to figure out this row to resource or row to thread allocation beforehand. And that's not trivial because, well, the matrices we're talking about have millions of rows, so it's not a trivial task. And there are existing approaches to this, so I'll take a look at what's already available in Rock BLAS, the ROCm library for BLAS. So the simplest approach is CSR general, which is pretty much what I showed in the very beginning. You allocate a fixed number of threads to each row, and then you just hope for the best. And that's really what you do, because this is fast, but only if all of the rows in the matrix are relatively short, so you don't have irregular sparsity. As soon as you hit irregular sparsity, you see what I visualized in the very first slides. Some of the threads take forever, so your overall runtime skyrockets. The second approach is kind of the other end of the spectrum. We scan the matrix linearly on the CPU with a single-threaded routine that builds up a metadata structure that allows us to have a kernel that's really fast because it allocates the correct number of threads to each row once it's on the GPU. So this is really fast multiplication for any matrix, but the problem is that we have to amortize this pre-processing over the course of many multiplications with the same matrix. And finally, there's a middle ground solution. It's called LRB. So here we parallelize some of the preprocessing and then dispatch different kernels for different row lengths, which gives us a semi-fast multiplication, so we amortize more quickly. And let's zoom in on that one a little bit, because that's what we're going to be focusing on. So the idea is to have separate kernels for the different row lengths, so we can kind of keep the divergence of the threads in check. And we parallelize the preprocessing by simply taking one thread per row and letting it compute the row length and then churning that through a log2. This gives us an implicit mapping of each row into a bin, and each bin then has similarly sized rows in it. And we can group these bins into different classes, basically. So the first couple ones will be stream, where a few threads are enough because the rows are relatively short. Then the second one, the rows are long enough so we can have a single thread group for each row. And finally, for very long rows, we can launch multiple thread groups that can then do local reductions first and then global atomics to do the final global reduction for the row. So for this specific example, we would end up with this mapping. We take the row IDs and we sort them into the bins. And then we can basically trigger a single dispatch for each bin, and we're fairly certain, or we are certain, that the row lengths will only diverge by a factor of 2, and that keeps our thread divergence kind of in check for the benefit of being able to parallelize this preprocessing. Now, while we parallelize the preprocessing, we still have this kind of back and forth that we see here, that the CPU needs to direct the entire thing, and we need to go over the entire matrix in order to perform that binning sort. And that's kind of unfortunate, because if we take a look at the problem again, what we see is that actually every single row is kind of independent from every other row. We only want to find out, based on the row length, how many threads do we need. And that's no row has any influence on any of the neighboring rows. So what we asked now is basically, what happens if we can inspect the row on the GPU and then directly launch a dynamic on-device relaunch, basically, of the required number of threads we need for a specific row, without having to wait for any kind of sorting mechanism or anything to happen, and without going back to the CPU. Well, this is where Workgraphs comes in, because that gives us exactly what we're looking for. It's dynamic on-device launch capabilities, and they are already available. The only issue, kind of, is that they are only exposed through graphics programming stacks, so such as D3, D12. But that shouldn't stop us, so let's take a closer look what actually happens in Workgraphs. We come from this world where the CPU directs what the GPU does, the GPU reports back, and then the CPU decides again what the GPU does next, and we go back and forth and back and forth. But if we take a closer look under the hood, we see that a GPU, of course, is made up of a lot of SIMD cores, but actually, there's also something called a command processor, which is a small RISC-V core, which basically handles communication with the CPU. So the CPU will send a kernel command, and the command processor takes care of decoding that and basically launching the threads that are required. So with Workgraph, we take advantage of having this RISC-V processor and basically cut out the middleman, let the CPU send over the entire problem description as a computational graph of different kernels. And then the CP will go ahead, launch the first kernel, but crucially now this kernel can talk back to the CP and basically enqueue further launch requests so that the GPU can basically feed itself, and we don't have to go back to the CPU as much, or anymore at all, basically. So the way Workgraphs exposes this on a very high level is you have your kernels are transferred into what's called nodes, but really it's just GPU kernel code, and we call it nodes now. And we have some API constructs available that let us send launch requests in the form of records. Records are user-defined data, so you can put anything in there that you want. But the semantics are, once you send a record, you request the system to dispatch a number of threads to process that record from one of the downstream nodes. These nodes tell the system how they want to be dispatched. Launch modes are what's the mechanism here. Broadcasting means a single record will want an entire grid to be spawned, to be consumed. With coalescing, you can define a number of records should be accumulated before a single thread group consumes all of them at once. And thread mode basically gives us a constrained version of this where we say a single record can be consumed by a single thread in isolation. So we don't have any constraints on how we group these threads. And here we have a lot of freedom in terms of scheduling under the hood because, of course, we want to aggregate these records before we actually launch these threads because we still need to utilize SIMD hardware well. So we can't just launch individual threads. That will be horrible. So the way this is done is, at least conceptually, every node has a queue that's managed by the system, and the system here is that small RISC-V core, the CP, and the special firmware that schedules, that does take care of all the Workgraph scheduling. So some of you may look at this and say, wait, we already have computational graphs on GPUs. They are called HIP or CUDA graphs, depending on your flavor of programming scheme that you want to use. And that's true, but they are decidedly not the same as Workgraphs. So let me spend a couple minutes explaining why. If we take a look at our sparse matrix again, we have this data dependency where basically we need to know the row length, and then we know how many threads we need to process it. And this is completely independent per row, so we actually don't care how large the matrix is in theory. Now, if we're in a task graph world, we have to build up a computational graph of kernels that define some kind of dependency. And the dependency being, we need to do a sort, and then we have kind of our, we have the rows sorted into the different bins, and then each bin can be consumed by a different kernel. So the dependency here is between the row sort kernel and the downstream consumer kernels. The task graph framework will pick this up and on the CPU record a command stream for you, so you don't have to worry about how that is actually resolved. But the key thing is that wait that's inserted. So we pre-record a command stream that basically tells the GPU to wait after the row sort, so all of the data dependencies are satisfied for the downstream kernels. But what we end up doing here is we scan over the entire matrix, even though we don't really have to because the data dependencies are much more fine-grained. We have to wait, and then we have the subsequent launches. And if some of those are empty because some of the row length classes we have aren't actually present in the matrix we're looking at, then we have empty launches that somehow need to be dealt with. And crucially, we aren't actually capturing the dependencies of the problem here, but of the solution, because we are only capturing dispatch level dependencies, even though our problem actually has much finer grained dependencies in the data itself. And that's because task graphs work on dispatches and not on the actual data dependencies. Now with work graphs, this is different, because now we can express that the actual thing we're doing is classifying each row, finding out its length, and then requesting a launch for that particular row of a downstream node. And that happens through the system managed data flow. And under the hood, what happens is we issue that single work graph command. The CP takes over completely and basically can decide to go through the matrix iteratively. So we only have to launch a couple of threads for the first row classifications. Once enough work has been accumulated, we can launch that right away, and then we can go through this process iteratively, leading to extremely intertwined computation based solely on the data dependencies, which in this case are very fine-grained. And if there's nothing ever produced for a certain class of rows, because they just aren't in the matrix, we don't launch anything for it. So we actually capture the thread group or even thread level dependencies at a very fine granularity with work graphs. So knowing all of this now, let's apply it to this logarithmic radix binning strategy. So basically we say a binning node takes a single thread per row and computes the row length, and through the log2 we determine which node is going to be responsible for that row based on its length. We send that row ID to the node directly for each thread, and then the different nodes declare how they want to be treated. So for very short rows, of course, we only need one thread or a couple threads, so we can use thread mode. For longer rows, we need an entire work group for each row, so we can use coalescing mode with different thread group sizes in the different nodes. And finally, for the very long rows, we can use the broadcast mode where we can launch multiple thread groups for a single row. And now the execution timeline looks something like this, where the CPU doesn't do a whole lot of preprocessing anymore, and the GPU under the hood, as we've seen on the prior slide, basically does this through the work graph scheduling. Now, I said before, this is implemented in our graphics driver, and that's what we had to do. We had to basically rip out the part of that support from our graphics driver, then somehow hook it up to an HPC research framework from our project partners at the University of Ingolstadt, which is called AnyDSL. And through a little bit of engineering and a little bit of magic, we made it work so that we could run our evaluation on real hardware. So we have a system with a Ryzen 9 and an RX 7900 here. We took 59 sparse matrices from the suit sparse, and what we see in this graph is all of our matrices and then the normalized GFLOPs and they're normalized to our baseline, which is the ROC sparse implementation of the LRB algorithm, so the compute version. And now we can see we didn't change the algorithm, we just changed to dynamic on-device scheduling, and we see a significant speed up here across the bank, basically. And to have some numbers on it, let's switch the view. It's pretty much the same data, but now we can see first in red, we see the average speed up is going to be 2.3 compared to the ROC sparse version. But to be fair, the ROC sparse general algorithm, remember that was the one where we basically take a couple of threads for each row and just dispatch them and hope for the best, actually works out pretty well for this test set. And that's because most of these matrices have very little variety in their sparsity. But what we see on the right-hand side of the graph is that the matrices with a lot of variety in the sparsity, CSR general actually deteriorates because you have long rows in the matrix, and that just doesn't work out well if you have a fixed thread allocation. But the work graphs version here still shows a consistent performance improvement. So switching to multi-iteration data, where basically you pre-process a matrix once and then you reuse it over and over with multiple vectors. What we measure here is on the x-axis, you see how we increase the number of multiplications, and we now have CSR adaptive, so the version that does a lot of CPU-based preprocessing and then has a quick multiplication. And we see why we don't use it for single iteration, because it has a huge cost of preprocessing, but that amortizes over time because we have more multiplications and they are pretty fast. So where we want to end up, obviously, is kind of the bottom right of this graph. So let's take a look. If we see our work graph data here, we kind of did it, but not really. We're faster for up to 10 iterations, but then we kind of lose out, even though we do the same thing as CSR LRB, and we thought we were faster, right? We actually aren't, because we don't do any amortization. And what I mean by that is that if we take our graph and we take a matrix into it, we produce the row IDs to the downstream nodes, we're done. But then on the second iteration, the graph doesn't change. We do the same thing over and over again. And that happens for every single iteration, even though the matrix doesn't change. So while we have huge benefits from overlaying all of that pre-processing and processing for a single iteration, it doesn't serve us well for multiple iterations. So what we did now was basically take the approach of, on the first iteration, counting a little bit to the side how many records we have for each row, then use a binning cache, so a separate allocation basically, into which we can then write these row IDs once. And then we have a basis from which we can then launch over and over again and simply reuse, because we know that the binning is not going to change because the matrix stays the same. So what we've effectively done here is replicate the data structure that the compute version of LRB builds up, but we've done it completely on the GPU, and we have hidden it under the first iteration of the matrix multiply. And that shows in the data. So when we add this version of our work graph here, we see that we consistently outperform the RockSparse compute baseline. So overall, what we glean from this is basically that by applying dynamic on-device scheduling and cutting out the CPU completely to an existing algorithm without really changing the algorithm at its core, we can yield substantial improvements. And at this point, we could have gone home and said, cool, nice, but I'm going to take 2 more minutes because we actually can do better. Because we took a look at why CSR general is actually much better for a lot of the matrices we looked at. And the simple reason is most of these have very little variability in their sparsity. So for very short rows, and if all of the rows in your matrix are really short, then really the best solution is just give each row a couple of threads and be done with it. It's fine. So our idea was to basically just default to that mode, and only if we find that one row might deteriorate performance because it's very long, we use work graphs to basically break this row out and request more threads to be launched to handle that specific row. So taking our graph that we already know here on the left, we basically took all of the code for the red and the green nodes, so the short and like the medium long rows, and moved them into the binning processing. And all that we do is take a look at the row lengths at the start, and we find if any of the threads would be ones that run very long, and they write out records to trigger node launches for those rows with more threads as needed, but the rest can happen in that workgroup right away. So with this, adding the green bar for that variant now, we can see that it's much faster than our initial work graphs version. So in numbers, we are now up to a 3.3 times speed up compared to the RockSparse LRB baseline. And again, we kind of keep our performance up relatively stable compared to RockSparse General, which is obviously pretty obvious because RockSparse General can't do that breaking out. Here we suffer from single threads running very long on very long rows. And switching over to multi-iteration, we can see that because this is much faster than any of our other versions, we can shift the amortization point of the much more advanced CSR adaptive far to the right to up to around 90 iterations. This depends heavily on which matrices you're combining. So come take a look at the poster or at the paper to see like a better, more detailed look at how this changes when you look at different matrices. But the bottom line is, with work graphs and its dynamic on-device scheduling, you have a great tool for dealing with unknowns. So we can detect and exploit subgrid data dependencies at runtime, and we can make fine-grained scheduling decisions at runtime. And by looking at SpMV, we've kind of demonstrated that these principles can apply to the HPC space. So even though it is a tool from the graphics space, let's see if we can make it work in HPC as well. And with that, thank you very much. I need to show this. And now I'm happy to take any questions.